Welcome back to the garage, guys. Been getting a lot of questions about the computer side of the running a CNC machine and what it takes and what's involved. We thought we'd shoot a quick video today to clear things up for those that still have questions. On the software side of things, there's three main components to a CNC machine. First one is you got to draw the parts. So you have to have a CAD software, computer aided drafting. The second one is you have to have a CAM software, computer aided machining. And the third one is you have to have a G-code sender to send that process to the machine. And there's also a fourth one, but it's not software. It's called firmware. So the first software type we're going to talk about is the CAD software, or the computer-aided drafting. So what that does is you have to have a software to draw your part in. So you got to design your part. You got to tell it the outer dimensions. You've got to have hole sizes, hole placements, everything you need, even part thickness. The part thickness comes into play when you set up your tools and stuff, but for right now, we're just going to talk about drawing the part. So there's lots of different softwares to draw a part. We recommend using Fusion 360, and that's what we take you through in the plans and tutorials. People draw in FreeCAD, people draw in Inkscape, people draw in other CAD softwares. It really doesn't matter where you draw the part. The main thing is that you come up with a DXF file. So that's the first piece to do. Now, we get questions about what type of computer or how powerful a computer or what are the computer requirements to run the CNC. Well, running the machine takes absolutely no computer power. Any type of device, basically with a USB output, will run it. An old computer, anything will run it. But what you need to have is you need to have a computer with enough power to run the drafting software or the CAD software, whatever you're going to use. That should determine what type of computer you need, not the other parts of the machine. So, because those don't take anything to run. So now we've talked about the CAD, we're going to move on to the second software. The second software is the CAM software, or the computer aided manufacturing. So now that we have the part drawn, we have this part, we have to tell the plasma cutter how to run around these points and how to lift up, move over, go around the circles, how fast to go, everything that the plasma cutter needs. With making the tool pass on that, the last thing that happens is it turns these tool paths into G-code, and you have to have a post processor to do that. Now, the post processor is specialized based on the type of machine you're running. So in our plans, we have a post processor to add into Fusion so you get the right output of G-code to send to the machine. We have the CAM running through the post processor. It creates the G-code that the machine is going to use. So we covered the first two software already. We're going to skip the third for just a minute. We're going to jump into firmware. Firmware we use is GerbelHal. And what firmware does, it takes the G-code and turns it into machine motion. So I'm holding a ESP32 controller, and we have to put GerbelHal, the firmware, into this controller. Now, GerbelHal has 50 different files and probably over 50,000 lines of code that need to be installed into this controller. Now, there's lots of ways to install the firmware in this. Installing firmware is also called flash. So in our instructions, we say you have to flash the controller. So you can use Openbuilds control, which we talk about in the plans. You could use Xloader. You could use Arduino IDE. You could use Espressif IDE. So there's lots of ways to get this in there. We try to simplify things like we did with Fusion so we can do the CAD and the CAM in one. So to install the firmware, we're going to use Openbuilds control, which we can flash, and we use that as the control software, which is the third type that we're going to talk about. Now, it's not a secret to many of you that Openbuilds, the parent company that made Openbuilds Control, is going out of business. They're going to lock up the doors and call it quits. Well, Openbuilds Control is an open source software, so that means it's available to anybody, and that will continue to live on. It won't be updated probably in the future, but there is already a repository on GitHub that has all the older versions already stored. We've already stored a copy, the latest copies that we need to run the machine, so don't worry about Openbuilds Control going away, affecting how you run your machine. So what is Openbuilds Control? Well, Openbuilds Control is a G-code sender. So that's all it does. It takes that G code that we created from the post processor and it sends it into the ESP32. That's all it does. You know, sure, you can move to home position, you can move a few things around, control the machine a little bit, but its primary function is just to move the G code to here. Now, you could do that with certain chips. You could take an SD card and physically grab it, plug it in. That's moving the G code to the controller. That's all Openbuilds control does. There's lots of G code senders out there. There's G sender. There's universal G code sender. Those are the big ones. Those are the popular ones. We just happen to use Openbuilds control because we can combine a couple things in there, the flashing and the sending. In our plan package, we have detailed explanations how to use Fusion for your CAD and your CAM, and also how to use Openbuilds control for your G code sender. Now, why did we choose those? Well, we already mentioned because they combine some of the processes, but the biggest reason we chose those is because they're free. Fusion is free for personal use. If you're using it for commercial side, you do need a license, but for personal use, it is free. That's why we chose those.
So what I have open right now is Fusion 360, and this is our CAD software. And this will be used for drawing our parts to make on our CNC machine. And this is a totally free software, and everything I'm about to do, you will be able to do with the free version or hobbyist version of the license. So I went ahead and I opened up a new design, and this is what will pop up. This is where we're going to be drafting all of our parts. So what I'm going to be doing is drawing a very simple plate to mount caster wheels onto. Every part that you're going to draw is going to start with a sketch, a 2D sketch. So I'm going to go to create sketch. And this is asking me what plane I want to make this sketch in. And I want to make this in the XY plane. You can see up here, the axes mean, the X is the red, the green is the Y, and the Z is the blue. So I want to create my part in the XY plane. So now that I'm in the sketch space, I'm going to start off by making a rectangle. And you can see up here, there's a few preset shapes that we can make. And then there's even more on this drop-down menu. So I'm going to start by making a 2-point rectangle. I'm just going to go vertex to vertex. And then here's my sketch dimension. So I'm going to give this rectangle some dimensions. I'm going to go 100 millimeters by 60 millimeters. That's going to be the size of our caster plate. Now what we need to do is make some holes to bolt on the actual caster wheel. So what I'm going to do is use the circle to make some holes. And we're going to put a circle up here with a diameter of, let's say, 8 millimeters. I'm going to go to all 4 corners and do that same thing. As you can see now, all 4 of the holes for our bolts to bolt on the caster are on our plate. But as you can see, I could drag these around wherever I want. They're not dimensioned. And that's actually what these blue lines mean versus the black lines. These blue lines are objects that aren't constrained. So I can just take these and move these around wherever I want. I can't with the black ones. So you'd have to put some dimensions in. Let's make these nice and square in the corner. We'll go 10 millimeters and 10 millimeters. And I can do the same thing on all 4 corners. But let's say I want some slotted holes, just in case I need some play in my casters. Well, how am I going to draw a slotted hole? Well, I'm going to do that with 2 circles. I'm going to make another circle, let's say here, with 8 millimeters in diameter. Now what I need to do is be able to connect these so it's a nice oval. So I can use my line tool to connect them. But these lines don't seem to match up very well. So what I can do to bring the line to the edge of the circle and make a nice oval shape is use this tangent tool. And I can make this line segment tangent to the circle. And that's what this line means here. So now that all these are tangent, I have a nice oval. but the oval still isn't defined. I can still drag these around and do whatever I want with them. So I need to put some dimensions on it. I want to keep this nice and square in the corner, so I'm going to use my dimensions to do that. Let's say this is 13 millimeters. And let's say this could be 8. And I'll just do the same thing with the other circle. So now that everything's black, you can see, you can kind of infer that there's that nice oval shape around here. And everything's black, so everything's locked and constrained. Now what I'm going to do is go and repeat this on all 4 of the corners. So you can see I have all my ovals drawn in the right locations and dimensioned. But now that I'm thinking this is kind of a sharp corner, and I want that rounded. So what I can do is use this fillet tool, and this will round off sharp corners like that. So I can select the 2 segments that I want to round off, and let's say give it a radius of 10. That looks better. I'm going to do that on all the corners now. Okay, that looks better. Now that I have the outline of the shape I want to make, I can go ahead and finish the sketch. And next, what I'm going to do is use the extrude tool to actually make this into a physical body and something that's just a lot easier to visualize. I'm going to go to create and extrude, and I'm going to select the areas that I want to give thickness to. And the sheet steel that I'm going to use is 3 millimeters, so I'm going to extrude this by 3 millimeters just to keep things consistent. So you can see this oval is now not part of our shape. I can go ahead and click OK. Now we have our caster plate. Now it looks like a part we want to make. Now that I have the part drawn, the CAD software that I used to draft this part is over with, and now I need to move on to the CAM software to generate the tool paths. Luckily, since we chose Fusion 360, these are both the same software. And all I have to do is go from design to manufacture, and now I'm in the CAD area. Or now I'm in the CAM area, excuse me. Now that I'm in the CAM area, the first thing I'm going to do is create a setup. And what this does is it defines the stock material I'm going to use and our origin coordinates. So I'm going to go to Setup, New Setup. So this kind of yellowish tan box is our stock that it automatically generated for us. And since we are plasma cutting, this isn't really that important. Since we're using just bulk sheet metal, we can kind of plop this anywhere on there that we want and it'll work just fine. What's a lot more important is the 000 position. And that's actually where all 3 of these line segments interact. You can see it's here. And what this will do is default to model orientation. So you can see up here our X, Y, and Z match our X, Y, and Z orientation here. And since in the previous step we drew our part on the XY plane, all this stuff is already lined up for us already. But the position of the 000 coordinate might not be in the best place. I generally like to put it in the corner of the part because it's a lot easier to set up and define that position in real life. So what I'm going to do is just click that point. And now when I actually start this job in real life, this will be my 0 point, and that's where I'm going to start the job from. So if you really want to, you can put in your stock dimensions. It's not that important since we are plasma cutting. If you wanted to nest your sheets really nice and tightly, this may be more relevant to you. But in the post-process, our work coordinate offset, that's what this stands for, has to be set to 1. Now that our setup is complete, I can actually go ahead and start making tool paths. So I'm going to go to the Fabrication tab, Cutting, and 2D Profile, since we're plasma cutting. I'm going to go ahead and select a tool. And If you already have a whole bunch of tools made, you can go to your local library and they'll all be there. But I'm just going to make a new tool for the sake of demonstration. I'm going to go to a plasma cutter. Let's just call this the demo tool. You could fill out all this information if you really want to. It's not necessary. What is necessary is your nozzle diameter and your kerf width. You're going to have to get these values from the manufacturer or where you buy your consumables from. These default settings look pretty good, so we're just going to keep them. The holder, you don't really need to fill out this information either. It's not really that relevant. The cutting speed, the lead in, the lead out rates are relevant. So let's just say we're going to cut at 3,000 millimeters a minute. Our cut height and our pierce height, they're not actually defined here. They're defined in a later step, but to actually make the tool, Fusion is going to require these. So we're just going to leave all this stuff at default now because it's going to be defined later on in the process. In the post processor, the default information here will also be fine. I'm going to go ahead and accept it, and then I'm going to select this new tool that we made. Now that I have the tool selected, you can see that our cutting feed rates are here and then our nozzle diameter. So what I'm going to go on to next is the geometry, and this is where we're actually going to set the tool paths that we want to make. And I can go ahead and select the part I want to cut out. And what this will do is allow Fusion to automatically generate what direction and what side of the line, these lines that are shown here, what side of the line to put the torch on. And this is going to be correct basically 100% of the time. And if you really want to, you can just select these individually. And do it manually if you want to. And you can see this little red arrow here. What this does is it shows you what direction the cutter is going to move and on what side of the line it's going to cut as well. And it looks like all of these are correct. So Fusion was right just to begin with. So we're going to go ahead and keep it like that. Now that I've selected all my contours or my parts that I want to cut out, I need to move on to the heights tab. And this is actually where the cutting height is going to be selected. And you could see this is the clearance height in orange, the retract height in green, and the top height in blue. This top height in blue is actually going to be your cutting height. So what I'm going to do is take this and give it to 1.5 millimeters. Above stock top doesn't really matter since we're resetting our 0 off the actual edge of the metal anyways. This retract height is going to be once we cut a path and our Z axis moves up, over, and across for the travel, this retract height is going to be how high we want to retract from. Typically, you'll want this between 5 and 10 millimeters. We'll go 10. And then this clearance height is the initial height when the job starts that it's going to come in on and then come back down. And then another 10 millimeters on top of that's typically fine. And then these lines help you visualize about how high stuff actually is. Now that that's done, we can go on to the passes tab. And most of this stuff you're just going to want to leave default as is. But what you can do is you can manipulate what side you want to cut on. If you want to cut on one side of the line directly on top of the line, you can use the left, center, and right. If you don't want to manipulate that at all, just always leave it as left, and compensation type you always want in computer. One thing I also like to do too is enable the smoothing, and what this does is it changes all of when it generates the G code, it changes all of the curved motions from little tiny line segments into actual arc commands, and it dramatically reduces the size of your G code files. Now that the passes is done, you can go on to links. And what this will do is you could set in your lead ins, your lead outs, and all that stuff. So I'm using a Z axis, so I'm not going to check keep nozzle down. If you only have a 2-axis machine, you want to select this, and what this will do is prevent the Z-axis from traveling over already cut out holes and things like that to prevent you from hitting tip-ups. So I'm not going to check that. What this section here will do is define my lead in and lead out rules. So I have a lead in radius of 0 millimeters. You could see if I have put a radius on it, it'll make a nice arc motion into your cut. And then I have 60 degrees here, and that will just depend on how sharp you want that initial lead in to be on. And then the 5 millimeters will define how far you want the lead in. And then you can have your lead out enabled if you want to, and then you can say, well, do I want my lead in and lead out rules to be the same? Almost always you're going to want them to be the same. So you can just say that they are. If you don't want to, you can define different rules here. My pierce clearance, I'm just going to always want to set to 0 because that's defined later. I'm just going to change this to, let's say, 12 millimeters, and then I'm going to hit OK, and it's going to generate our toolpath. So you can see here, we got a warning here, and it only ended up cutting the outside. That's kind of strange. The reason this did that was because it couldn't actually generate a toolpath given the rules that we created. So our lead out distance, remember how I changed that, is actually way bigger than what the size of these holes are. That's why it didn't generate the toolpath, because it couldn't based on the rules. So I'm going to drop that down to 5 millimeters. And let's say I want to define my start and stop points. Let's put them on these edges here. And right here. So now that I have my 5 start and stop points defined, I can go ahead and click OK. Or you can just let it generate those on its own. Now you can see I have all of the tool paths made, and that actually looks okay. I can go ahead and simulate this and kind of get an idea of how this will happen in real life. So you can see I'm coming down. I have my torch on. It's coming around. And that looks okay. And you can see our retract heights and our travel moves here in yellow, our lead in and lead outs in green, and our cutting of the actual part in blue. So I can go ahead and exit the simulation. So our simulation's done. Our tool paths look good. But now how do I get these onto the machine so the machine can do something with them? Well, we need to use a post processor. And what the post processor will do is convert these tool paths into G code, which the machine will read and turn the G code into actual physical movements. So I'm going to go ahead and post process. So up here on this first line is where you select your post processor, and what this will do is convert the tool paths into actual G code, and you can go ahead and select it here. The one I'm using is included in the plans. I'm just going to name the file. I'm going to call it test caster plate. I'm going to select my output folder. My desktop's fine for now. My unit, I'm going to always want to put this or leave this in document units. And what this does is it just allows Fusion to convert or make all the unit conversions on its own. So over here are the settings that I'm actually going to use to post my code, and only some of them are relevant for plasma cutting. This first one here is the plasma pierce delay, and this is the amount of time I'm going to allow the plasma cutter to take to cut all the way through the metal before I start moving horizontally. This next one, I'm going to want to set to 10, and this is the amount of clearance that I just added clearance I want to have when I start the job. I'm going to want to disable, not check this box, the G53 coordinates. They're not relevant for plasma cutting. I also want to disable the linearized small arcs. What this will do is allow me to take advantage of that smoothing function. These next settings here are only relevant if you're using a Z-axis. If you're not using a Z-axis and only have a 2-axis machine, just declick those and then go ahead and post. Since I am using a Z, they're relevant. This first one is my plasma pierce height. This defines how high off the metal that I actually want to do the pierce. 3.5 millimeters, or about 3/16 of an inch or so, is pretty okay. The second one is my probe offset, and this is defined by the distance from when the tip of the plasma torch first touches the metal to when the probe actually senses that the metal's there. On our design, it's about 1 millimeter. Yours might be a little bit different. It might be 1.1, 1.2. You're gonna have to calculate this distance on your own. Now, once I have all the inputs made, I can go ahead and post my code. Now you can see, here's the code that I posted, and these are the actual machine instructions that the machine uses. And you can see these G3 commands are the arc commands that the smoothing function did. So if we didn't enable smoothing, it'd be a bunch of these G1s. It could be like 100 of these per G3 command. So this is Openbuilds Control, and this is the main software that we are going to be running the plasma table with. But before you can run the plasma table, you need to connect the machine. And Openbuilds Control supports various types of connection, whether you want to be over USB, Wi-Fi, Bluetooth, Ethernet. You can do all of those. I have the machine configured to run over Wi-Fi right now, so I'm going to select the machine IP address and then click connect. You can see down here on the serial monitor that everything was okay, and you could see on the second camera that I now have control over the machine. So over here you can jog the machine, and you can set your jog speeds here. So I could jog my Y-axis, my X, and my Z. And I can even go to incremental jog if I need that for whatever reason, and I can run in 10 millimeter steps, 100, 1, and even 0.1 millimeters. I can even change to inch mode here if you prefer that, but I'm going to stick with millimeters. I can set my machine zeros. I can go to 0. Let's say if I were to just jog the machine forward, I need to go back to 0. I could tell it to go back to 0. I can open up my G-code files here. I already have one open, and it's that caster plate, so I could see the job, what the job looks like. It looks really similar to Fusion. We can see our travel moves and our cutting moves there. And I can even see what the G-code looks like. If I need to make a update or anything like that, I can just edit it right here. On this second tab here are the Gerbil settings. I want to go to the advanced settings for on our machine, and basically what these are how you would configure Gerbil how to run on your machine. This next tab here is our troubleshooting tab, and this will tell us if we have any issues or with our sensors or our limits or anything like that. So we have our X, Y, and Z limits, our probe, and then our door sensor, which you can also use as your e-stop. And now we're going to go ahead and start the job. So I already have this caster plate loaded. So the first thing I'm going to do is send my machine to home with the home all. Okay, now that the machine is homed, what that does is it sends it to a predefined hard stop limits. So I'm going to jog the machine to the point that I want to start the job at. Let's say here. And then I'm going to set 0. And then I can just go ahead and run the job. So that's it. That's pretty much all there is to running Openbuilds control.
All right, guys, we hope that clears a few things up. Remember, there's three main types of software. You have a CAD software for drawing parts. You have a CAM software for creating tool paths. You have a G-code sender that takes the G-code and sends it to the machine. And remember, the machine runs on firmware. So remember those points. The last point I want to stress again is if you're looking for a new computer, or if you're wondering if your computer will work with our system, don't base it on our system. Base it on the CAD software that you intend to run to draw your parts. With that, thanks a lot for watching to the end, and make sure to like and subscribe.